Hello and welcome to the fourth video in the Machine Learning Foundation series. Today we will discuss linear least squares regression. Before the advent of deep learning or its easy to use libraries, linear least squares regression and its variants were one of the most widely deployed regression approaches in the statistical domain. It is one of the easiest to implement machine learning algorithms. In this video we will discuss the main objectives of linear least square regression, an example that will help us start to understand how we should interpret the coefficients of a linear least squared regression model, and also build a linear least squared regression model using Python. Let's get started. Make sure to watch the video all the way through for a complete understanding. Least squares linear regression or regression models in general have two main objectives. First is to establish if there is a relationship between two variables, like if one increases, the other increases as well. And conversely, if one of the variables' value increases, the other variable's value tend to decrease. More specifically, we are going to be talking about a statistically significant relationship between two variables. Let's talk about some real-world applications for this algorithm. Businesses often use linear regression to understand the relationship between advertising spend and revenue. Suppose we have a scatter plot for the business's revenue versus advertising spend that looks somewhat like this. It's easy to note that if the advertising spend increases, the revenue also increases. Now, if you are the one in charge of analyzing this data, you can fit a linear regression model and establish if a relationship between the revenue and advertising spend exists. The blue line represents our linear regression model. We'll go over it in greater detail later in the video. Another example could be of a medical researcher who can analyze and test if there is a relationship between drug doses and the blood pressure of patients. We could ask if an increase in dosage is associated with a decrease in blood pressure. We can use the regression model to test if that relationship exists. Another example that I hope you find odd is the relationship between a student's height and the same student's exam score. We should expect no relationship to exist. That is, we cannot fit a straight line onto these red dots, and we can use regression model to establish that. Our second objective is going to be to forecast new observations. What I mean here is, can we use what we know about an existing relationship to forecast unobserved values? For instance, if a company awards salaries based on the experience of an employee, and if we have the data that reflects how much salary different employees with different years of experience get, we can predict the salary of some new employee that joins this company and reward them based on their experience. Similarly, let's say that you want to run a sales forecast to understand if having your salespeople make more sales calls will mean that they close more deals. To conduct this forecast, you need historical data that depicts the number of sales calls made over a certain period, and you can forecast the number of calls required to make a given number of sales using a regression model. When we use linear regression models, we call them linear because the magic is that we are using a linear equation. And from your high school years, you might remember one of these. You have definitely seen this equation before, right? This is the equation of a straight line. Here, y is a function of x, and there is a term that is added to the function. Another one that multiplies the x. In the statistics world, they like Greek letters, so they use a slightly different notation. The same linear equation is going to have a beta 0 term, which is called the intercept or the constant, and a beta 1 term, which is the term that multiplies to x, and we call it as the coefficient of x or the slope of x. The machine learning practitioners gave this equation a new look and used a different notation. Our linear equation is going to have a b term, which is called the bias of the model, and a w which multiplies to x, and we call it the weights or parameters of the model. The parameters are n-dimensional vectors just like the input, and the bias term is a real valued scalar. Also, we now have a hat over the y, and it is read as y hat. This y hat denotes the estimated output by our linear model. And as a recap, we call these linear equations because they will appear as a straight line. Now we are going to be talking about two different roles that variables play in regression models. Suppose we are analyzing the experience versus salary data that looks like this. The same equation can be rewritten as salary equals sum of weight times experience and the bias term. The salary or the variable x is also called the dependent variable. This is the variable whose values you want to explain or forecast. We call it the dependent variable because its value depends on something else, and we will be denoting it as y hat. The other role is that of the independent variable, that is experience in our case, and this is the variable that explains the other one. We say that its values are independent, hence its name. We will denote this variable as x. Now let us try to understand the effect of changing the weight W and the bias B of the linear model. That is the blue line in a univariate setting where x, W and B are all real valued numbers. Notice how the predictive model or the line moves away from the origin as the bias value changes. If the bias value is 1, the line is parallel to the input axis and intersects the output axis at 1. The intercept value can also be a negative number, which means that the line intersects the y-axis at the negative value but remains parallel to the input axis. We had fixed w at 0 for the last few examples, and you must have noticed that the function wx plus b remained parallel to the input axis. Its distance from the input axis was controlled by the bias term. This is to be expected as the values of the x stop having any influence on the output y. Now let's see how changing the weight or the parameter value changes the line. Notice that the weight W has the net effect of rotating the predictive model or the line about the intercept. I hope that you have figured out that with the right set of W and B values, we can have a model that can best predict the values of the dependent variable given the value of the independent variables. And we can trust our instincts and scatterplot the data on a graph, just like we have been doing, and find the line that we think best fits this data and use the function to explain or forecast observations. Let's try it. Let's find a suitable W value such that the line is parallel to most data points and then tweak the B value so that the line best fits the data. I think this is as close as we can get when intuitively placing the line. Maybe we found the correct line, but in reality, math and statistics tend to go beyond where the eyes meet the graph. It is usually risky to rely solely on scatterplot to assess the quality of the model. So to find the best values of W and B, we train our model and the model learns these values by itself. We will come back to how the model learns this value, but for now, let's extend this behavior to a multivariate setting because most outcomes in this world do not depend on a single variable. There are multiple variables that are responsible for the outcome of most real-world scenarios. A multivariate setting is quite similar to the univariate setting we discussed previously, but with multiple independent variables contributing to the dependent variable. Since there are multiple variables involved, it is impossible to represent all of them on a two-dimensional graph. So I want your full attention for this section. I hope you remember this equation from the last slide. In a multivariate setting, this equation would be rewritten as, now you can think of it as we are trying to examine the relationship between salary and experience, the highest level of education, the university they went to, their role in your company, etc. There could be many more. So the coefficients of these independent variables represent the weight vector. Let's see a few more examples. Suppose you run an e-commerce company that has collected the data of its customers, such as age, purchase history of a customer, gender, and company, and want to find the relationship between these different independent variables and the dependent variable. You can use a multivariate linear regression model to explain or forecast observations. Another example could be suppose you want to estimate the price of a house. You will collect details such as the location of the house, number of bedrooms, size in square feet, and amenities available or not. Based on these details, the price of the house can be predicted and how each variable is interrelated. Also, economists can use multivariate regression to predict the GDP growth of a state or a country based on the parameters like the total amount spent by the consumers, import expenditure, total gains from export, total savings, etc. Let's see how we approach a multivariate linear regression problem. For the sake of a clear explanation, let's consider two independent variables, experience and the highest level of education. So the equation can also be rewritten as y equals beta 1 times experience and beta 2 times the highest level of education. And the goal is to optimize all these coefficients such that the resulting equation best fits the data. Notice that the result will still be a line since the equation doesn't have any variables whose exponent is greater than 1. In a multivariate setting, the weight is a vector of real valued numbers. Different values in this vector represent the effect of different variables on the output. In our case, we are considering a two-dimensional vector, that is, we have two dependent variables whose coefficients are denoted by the value in the W vector. You can think of this setting as we are trying to examine the relationship between the salary of an employee given their experience and highest level of education. So there are two independent variables here, experience and the highest level of education. The value in W, that is 0 and 1, we can say 0 is the coefficient for the experience and 1 is the coefficient for the highest level of education in the linear equation. Being a multivariate function, we represent W transpose W plus B as a colored plane over the input feature space to indicate variation in the values of the linear model as a function of the input features. To better understand the multivariate function, it is beneficial to look at it from the univariate perspective along each input axis, x1 and x2. We will again control the W and B terms to understand the effect of changing the weight vector W and the bias B on the predictive model. Observe that the weight vector W, as before, controls the direction of the growth of the function, the so-called gradient. Also, when one component of W is set to 0, for example, W equals 1, 0, so the corresponding perspective, that is x2 equals W transpose x plus B, becomes parallel to the corresponding input axis. Also note that the bias term again plays the role of moving the function plane away from the origin. A linear regression model's main aim is to find the best fit linear line and the optimal values of bias and weight such that the error is minimized. The error is the difference between the actual value and the predicted value, and the goal is to reduce this difference. The vertical distance between the data point and the regression line is known as the error or residual. Each data point has one residual. Suppose L denotes the training set consisting of L training instances. If y hat L denotes the prediction of the model for the instance xl yl, then the squared error can be given as this equation, where we simply subtract the predicted value from the actual value and square the output. And the sum of all the differences is known as the sum of residuals or errors. Therefore, the overall loss can be given by taking the sum of all such values. The predictive model for which this error value is the minimum is used to explain or forecast the value of the dependent variable. Note that the data does not perfectly lie along any of these lines. There is some inherent noise, a scenario common to all machine learning problems. For a complete understanding, let's talk about the maths behind it. We already know that the overall loss or the cost function is given by this formula. A simpler representation or hack that simplifies computation and implementation of this cost function involves extending the input vector x with a leading 1, such that x dash equals 1, x. As a result, the bias term p can be included in the parameters vector such that w dash equals b comma w. It is simple to prove that x dash transpose w equals x transpose w plus b. So mathematically this notation is correct and hence we can use it. To keep the presentation clear and concise, we will use the notation x to denote x dash and w to denote w dash in the remainder of this video. Now let's see how the error function is minimized. In the matrix notation, the sum of squared errors can be rewritten as this equation. Here x is a matrix containing the training instances such that the row of x is a training instance xl for all L. Similarly, y is a vector containing the target variable yl for all L. Note that the loss function is a quadratic function of the parameters w. Therefore, its minimum always exists, but it may not be unique. Being a quadratic function, we find the minimizer by differentiating with respect to the parameters of the model w. Setting the derivative to 0, the resulting normal equation can be given as this equation. If x transpose x is non-singular, therefore invertible, then the unique solution can be obtained by rearranging the terms of the above equation as: what if x transpose x is singular and hence not invertible? We deal with this using the ridge regression, which is still a linear model for regression. Let's get started with some coding. In my previous video, I recommended learning Python and I remember sharing a few tutorials as well. So today I am hoping you know basic Python and we can start coding these algorithms. Let's get started by creating a new notebook.
Jupyter notebooks make it very easy to tinker with code and run it in bits and pieces. As a result, they are widely used in scientific computing, and I will be using them in majority of our videos.
So this is your first time implementing the linear regression using the normal equation. So let's start by discussing the variables that we will be using and their shapes. We will use m to denote the number of training samples. That is, we will have this many data points in our training set. We will use n to denote the number of features or independent variables. Which leads our input matrix x to have a shape of m, n, that is size of training data, number of features. I would be a m cross 1 vector of real values and w would be a n cross 1 vector of real values. I hope that was easy to derive after our last example. Now let's import numpy as np and build our fake dataset. We will use the np.random.randn function that returns random values from a standard normal distribution. We also need to pass in the shape of the array. In our case, that will be m, n. Let's create a fake function that is y equals 3 times x and add some noise so that the model just doesn't return us 3 and 0. I think that will do it for our example.
Let us now plot the data that we generated using the matplotlib library. I also left a NumPy and matplotlib tutorial contributed by Professor Justin Johnson for Stanford's CS231N course in the description. Even if you have worked with Python and NumPy before, I highly recommend checking it out.
Now what we are going to do is define our linear regression normal equation function and we are going to send in x and y. First, let's create the vector of 1 for the bias term. So we will do b equal np.ones since it returns a vector with 1 given the shape, and we will send in x shape 0, 1 because we need it for all the training examples. Now we will use the hack that we talked about and add this vector to x using the np.append b and x along the axis 1. Which just says add it along the features. Now each training sample will have an additional value that will be 1, which is for the bias term. Now we can calculate w according to the normal equation that is on the left. Let's use np.linalg, which is a dedicated submodule for linear algebra in NumPy. And we will use the inverse function from there to calculate the inverse of x transpose dot x, and again take the dot product with x transpose dot y to complete the equation. And then we will return w. So that's our function. Let's call our function and verify if our function is any good. So the values that are returned here, which is sort of what you would expect.
Remember that we defined our y as 3 times x plus some random noise, and y hat comes pretty close.
If you were to write what y hat looks like, it would be this function.
Let us plot y hat on our data and visualize the results. Looks a good fit to me.
There are different optimization algorithms that can be used to optimize W and B values, like the gradient descent algorithm that we will see in later videos. Gradient descent is one of the most popular optimization algorithms and is very widely used in lots of different machine learning problems. The gradient descent method is less expensive to compute and scales better to larger data sets than the normal equation method. Can you guess why? Notice that this normal equation has a matrix inversion in it, and inverting a matrix is an expensive operation. If the number of samples is say less than 100, then it is quicker to use the normal equation than gradient descent. But in real life it is easily greater than 1000 and the sample size will be greater than 100k. Therefore gradient descent algorithm is more popular. We will discuss more efficient techniques in future videos, so stay tuned because we are only getting started. Congratulations on learning your first machine learning algorithm. We will end this video here. Give yourself a pat on the back. You deserve it after watching this video all the way through. That is all for this video. I'll meet you in the next. Don't forget to leave any questions, comments or suggestions in the comments. Thank you for your time. Have a wonderful day.